Welcome to ArXiv Preprint Server Daily, AI Frontiers. Today's episode focuses on recent advances in machine learning research, where we'll be synthesizing key trends in AI research. This presentation explores cutting-edge machine learning research from the ArXiv Preprint Server, identifying emerging themes and methodologies that are shaping the field. We'll analyze breakthrough approaches across various AI domains, from large language models to graph neural networks and beyond. Additionally, we'll highlight the implications these advances have for future research directions. Join us as we navigate through the latest developments that are pushing the boundaries of what's possible in machine learning research. Let's begin with an overview of the current machine learning research landscape. Machine learning research spans diverse subfields including large language models, LLMs, graph neural networks, and reinforcement learning. Current research primarily focuses on addressing key challenges in the field, particularly model efficiency, interpretability, and generalization capabilities. One notable trend is the increasing prevalence of interdisciplinary approaches that combine techniques across machine learning subdomains. Researchers are no longer siloed within narrow specialties but are instead drawing from multiple areas to create innovative solutions. Additionally, there's a growing emphasis on responsible AI development and deployment, reflecting the maturation of the field and recognition of AI's broader societal impacts. The first major research theme we'll explore is large language models. LLMs continue to dominate as a research focus with significant innovations in architecture design. Recent papers show considerable efficiency improvements that address computational constraints, making these powerful models more accessible and deployable. Researchers have developed novel pre-training objectives that enhance model capabilities beyond what was previously possible. Another important development is the emergence of specialized LLMs designed for domain-specific applications, moving beyond general-purpose models to those tailored for particular fields like healthcare, legal, or scientific research. Finally, there's a growing focus on mitigating biases and improving factuality in these models, addressing some of the most significant challenges in their practical application. The second research theme focuses on graph neural networks. GNNs are evolving to better capture complex structural relationships in data, moving beyond earlier limitations. New architectures are improving expressivity beyond traditional message passing limitations, allowing these networks to represent more sophisticated patterns and relationships. Applications of GNNs are rapidly expanding into scientific domains, particularly molecular modeling and physics simulations, where relational data is abundant. An interesting trend is the integration of GNNs with other machine learning paradigms to create hybrid approaches that leverage the strengths of multiple methodologies. Finally, significant scalability improvements are enabling the application of these powerful techniques to increasingly larger graphs, opening up new possibilities for analyzing complex networks and systems. Our third research theme examines interpretability and explainability in AI systems. There's a growing emphasis on understanding model decision-making processes, moving beyond the black box paradigm that has long characterized many machine learning approaches. Post hoc explanation methods are becoming more sophisticated, offering better insights into already trained models. Simultaneously, inherently interpretable model architectures are gaining traction, designed from the ground up with transparency in mind. Human-centered evaluation metrics for explanations are emerging, recognizing that explanations must be useful and comprehensible to human users, not just technically accurate. The field is actively working to bridge the gap between theoretical interpretability and practical usefulness, ensuring that explanations actually serve real-world needs. The fourth research theme covers federated and distributed learning approaches. Federated learning methods are increasingly addressing privacy concerns in sensitive domains like healthcare and finance, allowing models to be trained across multiple data sources without centralizing sensitive information. Novel communication-efficient algorithms are reducing bandwidth requirements, making these approaches more practical in real-world settings with limited connectivity. Heterogeneity challenges in federated learning are being tackled with adaptive optimization methods that account for differences in data distributions across participants. Integration with differential privacy techniques is providing stronger guarantees for user data protection. Finally, cross-device applications are expanding beyond mobile devices to Internet of Things, IoT, and edge computing scenarios, bringing machine learning capabilities to a wider range of distributed systems. Looking across the research papers, several key findings emerge. Efficiency-focused techniques are yielding comparable performance with significantly reduced computational resources, democratizing access to advanced AI capabilities. Multimodal approaches that combine different types of data consistently outperform single-modality methods, suggesting the importance of diverse information sources. Data quality is increasingly prioritized over quantity in model development, with researchers finding that carefully curated datasets often outperform much larger but noisier alternatives. Hybrid architectures that combine the strengths of different model types are showing particular promise, leveraging complementary capabilities to achieve better overall performance. Finally, real-world deployment considerations are increasingly driving research priorities, with practical constraints shaping the direction of theoretical advances. When examining methodological approaches across recent papers, several common techniques and evaluation practices stand out. Benchmark diversity is expanding beyond standard datasets to include more realistic real-world scenarios, providing better indicators of practical performance. Ablation studies are becoming increasingly rigorous to isolate the contribution of individual components, supporting more precise understanding of what drives performance improvements. Computational efficiency metrics such as flops and parameter count are now commonly reported alongside accuracy, reflecting the growing importance of resource constraints. There's a stronger emphasis on reproducibility with more detailed experimental protocols and code releases, enabling better verification and extension of research findings. Finally, broader impact assessments are becoming standard in methodology sections, reflecting increased awareness of the ethical dimensions of machine learning research. Let's examine our first selected paper, which focuses on advancing large language model capabilities through architectural innovations. This seminal work introduces a novel attention mechanism that scales linearly with sequence length, addressing one of the key limitations in previous transformer architectures. The approach demonstrates a remarkable 30% improvement in long context understanding tasks, enabling better comprehension of extended documents and conversations. It reduces computational requirements by 40% compared to previous state-of-the-art models, making deployment more feasible in resource-constrained environments. The paper introduces an innovative pre-training objective that combines multiple learning signals, creating more robust representations. Comprehensive ablation studies validate each architectural choice, providing clear evidence for the contribution of individual components to overall performance gains. Our second selected paper focuses on graph neural network evolution, specifically breaking through previous expressivity limitations. This work addresses fundamental limitations in GNN expressivity through a novel architecture that can capture more complex graph structures. The authors introduce a theoretical framework that formally proves the enhanced representational capacity of their approach compared to traditional GNNs. The method demonstrates state-of-the-art performance across molecular property prediction benchmarks, with particular improvements on complex molecules. Despite its increased expressive power, the approach maintains computational efficiency, making it practical for real-world applications. The paper also provides interpretable visualization of learned graph representations, offering insights into how the model captures structural information from the input graphs. The third selected paper presents breakthroughs in interpretability, effectively bridging the gap between performance and explainability. It introduces a novel framework that unifies post hoc and inherently interpretable approaches, creating a more comprehensive solution to the interpretability challenge. The authors develop human-aligned explanation metrics that have been validated through user studies, ensuring that explanations are actually useful to human operators. Their approach demonstrates explanations that maintain fidelity even for complex model decisions, where previous methods often failed. Remarkably, there's minimal performance trade-off, less than 2%, compared to black box counterparts, challenging the notion that interpretability necessarily comes at the cost of accuracy. The framework is applicable across diverse model architectures and domains, providing a versatile solution to the interpretability problem. Looking toward the future, several promising research directions are emerging. The integration of multimodal capabilities into unified architectures is becoming increasingly important, allowing models to process and reason across different types of data simultaneously. Resource-efficient AI is becoming critical as model sizes continue to grow, with researchers exploring various approaches to reduce computational and environmental costs. Standardization of trustworthiness metrics across the research community is gaining momentum, enabling more consistent evaluation of model reliability and safety. Domain-specific adaptations of foundation models are gaining importance, tailoring general capabilities to specialized applications. Finally, collaborative human-AI systems represent an emerging research frontier, focusing on how AI can most effectively augment human capabilities rather than simply automating tasks. In conclusion, several key takeaways emerge from our synthesis of the current state of machine learning research. Efficiency and scalability innovations are enabling broader AI applications, democratizing access to these powerful technologies. Interpretability research is maturing from theoretical explorations to practical implementations that can be deployed in real-world systems. We're seeing accelerated progress across machine learning domains due to cross-pollination between subfields, with techniques from one area often finding novel applications in others. Finally, responsible AI considerations are increasingly integrated into core research, rather than being treated as an afterthought, reflecting the field's growing maturity and awareness of its broader impacts. This research synthesis was created using AI tools including GPT and Claude 3.7 Sonnet 20250219, showcasing how AI can assist in research communication and knowledge dissemination. Text-to-speech synthesis was performed using Amazon Polly to create the audio you're hearing now. Visual elements accompanying this research were generated using Stable Diffusion, demonstrating the capabilities of modern image generation systems. All generated content was reviewed and validated by human machine learning research experts to ensure accuracy and relevance. This presentation is part of ongoing efforts to make cutting-edge research more accessible to broader audiences, bridging the gap between specialized academic work and practical understanding. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from ArXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.